What I'm going to do in this experiment is I'm going to investigate the current going through a very simple series circuit. So to start off with, I'm just going to have one lamp here, and if I just connect these wires in there, you can see that the lamp lights, the electric current is leaving the power supply, going through the lamp, and then it's coming back to the power supply. What I'm going to do now is I'm going to insert a couple of ammeters here to measure the current. So this is an ammeter, and I'm just going to replace this wire with an ammeter. Remember, an ammeter measures the current going through a component. So you can see that in this case we've got nearly 0.1 amps flowing through this ammeter. And I'm going to replace this one with another. What you can see straight away is that the readings are the same. This one showing minus. Just tells me the direction the current's going. If I switch the leads round, it comes out. So one common misconception by pupils is that current is used up as it travels around the circuit, and this isn't actually the case. What happens is that the same number of electrons leaves the power supply as enters on the other side. So the current is the same all the way around the circuit. We haven't gained or lost any electrons on the way round, so the current is identical going into the lamp and leaving the lamp. And we can test that theory out by adding some more components. So I'll just take this ammeter out, and I'm going to add in another lamp, like so. Put a lead in. So now I've added another lamp. So before it was reading 0.1, I'm just going to switch this one in, and what you can see now is that the current is lower on both ammeters. So 0.07, 0.07. So the current is lower, but it's still the same. So the same current is going in to the lamps as is coming out. It's the same current all the way around the circuit. And there's a lower current than before because I've added another lamp in here. So I've added some extra resistance. So I've now got two lamps rather than one. And if I add a further lamp into here, the current will drop down even lower. So if I switch that on, you can see all the lamps are dimmer than they were when there was just one lamp, and the current is now 0.05, 0.06, so it's going between the two. So the current is smaller because I have three lamps in there now in this series circuit, but the current is the same at all points around the circuit. Let's just take the ammeters out a second. So when we have the three lamps, there is more resistance. There are three lamps here, so there's a greater resistance as less current can get through. But as I was saying, is that the current is the same here, or here, or here. At all points, it's the same electric current flowing around the circuit. In the first experiment, we set up a series circuit with just one lamp here. So we've got an ammeter, and then a lamp, and then an ammeter. And we took the recorded the current going through each ammeter, and this was 0.10 amps, and this was 0.10 amps. And what that tells us is that the current going into the lamp is the same as the current leaving the lamp. And if you think about it, there is only one route for the electrons to take around this circuit. If I draw that route in, so it can go around this way, like so. And so the electric current can only flow around that one route. So we can't use up electrons, so the number of electrons that enters the lamp equals the number of electrons leaving the lamp. They've lost some energy because they've supplied it to the lamp, but the number of electrons is exactly the same. Now added a second lamp, so here's lamp 1 and here's lamp 2, and what we found was that the current had reduced, so it had gone from 0.1 amps to 0.07 amps. So the current is smaller in the circuit, and you would expect that because there are now two lamps, so there's more resistance in the circuit. So less electrons less current can flow through the circuit. But what we see is, again, the current going into the two lamps is the same as the current going out of the two lamps. So the current isn't used. It's the same around the circuit. Same at all points around the circuit. If I put an ammeter here, it would also read 0.07. So the current doesn't get used up. It's reduced because there's more resistance in the circuit. Finally, what we're going to do is add a third lamp into the circuit and check whether our rule is correct. So we're expecting a third lamp to have a smaller current, but to still have the same reading going into the lamps and out of the lamps. So we've now added a third lamp, 1, 2, 3 lamps, and the current's gone down again, and now it's reading 0.06 amps. So as expected, the current is smaller because there's more resistance in the circuit, but it's still the same going into and out of the lamps. So the current in a series circuit is the same at all points. That's our conclusion. The current in a series circuit is the same at all points. And that's our conclusion. In the first experiment, we set up a series circuit with just one lamp here. So we've got an ammeter, and then a lamp, and then an ammeter. And we took the recorded the current going through each ammeter, and this was 0.10 amps, and this was 0.10 amps. And what that tells us is that the current going into the lamp is the same as the current leaving the lamp. And if you think about it, there is only one route for the electrons to take around this circuit. If I draw that route in, so it can go around this way, like so. And so the electric current can only flow around that one route. So we can't use up electrons, so the number of electrons that enters the lamp equals the number of electrons leaving the lamp. They've lost some energy because they've supplied it to the lamp, but the number of electrons is exactly the same.